Title: Train Attention. Meta-learning, where to focus in continual knowledge learning. Abstract: This paper introduces a novel approach to continual knowledge learning, (CKL), in large language models, named Train-Attention-Augmented Language Model, TAALM. It enhances learning efficiency by dynamically predicting and applying weights to tokens based on their usefulness, utilizing a meta-learning framework. This method aims to mitigate catastrophic forgetting by focusing learning efforts on important tokens. Introduction. Large language models have shown remarkable effectiveness in various tasks but often suffer from catastrophic forgetting when new knowledge needs to be updated. The field of continual knowledge learning, CKL, is being researched to address this issue. Previous approaches include regularization, architectural modifications, and rehearsal techniques. However, these methods inherit the inefficiency of standard fine-tuning procedures, applying uniform weights to all tokens regardless of their importance. Train-Attention-Augmented Language Model, TAALM. The authors propose TAALM, which predicts weights of each token based on their usefulness, leveraging this weight on the training phase to enable efficient update of new knowledge. Train-Attention, the supportive model that predicts weight for the base model, is trained through the metalearning method. The concept of selecting important tokens has been explored outside the domain of CKL and demonstrates enhanced performance on downstream tasks. New benchmark. The authors also introduce a new CKL benchmark, LAMA-ckl, designed to offer a more clear comparison of learning and retention performance. This benchmark's advantages over the previous standard are explained in the paper. Experiments conducted on LAMA-ckl and previous CKL benchmark, Temporal Wiki, show that TAALM achieves remarkable state-of-the-art performance on both. Contributions. The main contributions of this paper can be summarized in 3. 1. Proposing a novel token weighting approach to the CKL task, with a novel problem definition in metalearning method. 2. Introducing a new CKL benchmark, LAMA-ckl, and 3. Achieving state-of-the-art performance on both LAMA-ckl and previous CKL benchmarks, and showing synergistic compatibility when integrated with previous CKL approaches. Continual knowledge learning, CKL, is a variation of continual learning, CL, that focuses on updating new knowledge without catastrophic forgetting of previously learned and preservable knowledge. This paper introduces a new benchmark for CKL based on the LAMA dataset and presents a novel method called Train-Attention-Augmented Language Model, TAALM, which significantly improves over baselines through extensive experiments. The 3 main approaches for CL and CKL are regularization, architectural, and rehearsal. These methods share a common goal: minimizing changes in parameters from initial points. Our proposed methodology assigns weights to log probabilities of each sequence, approximating the importance of each sequence, named token importance. We define token importance as usefulness, indicating how much the contained information is useful for solving related tasks in the future. A metalearning approach can be derived to develop a supportive model, meta-learner, that predicts the optimal token weights. Let theta represent a base causal LM that continually learns knowledge and solves tasks. Training dataset D is a set of pairs of D and TD, where TD represents a task that can be solved using information contained in D. The meta-learner, named Train Attention and denoted as phi, predicts WD from D as illustrated in Figure 2a. Phi inherits the architecture and pre-trained parameters of the causal LM, but the decoder layer is adjusted to yield only a single-dimensional float between 0, 1, for each position. The desired process, learning knowledge and solving a task, is described in 2 steps. A. Learn. Theta is trained on D and is updated to theta, with a token weight WD, phi left pointing arrow phi, D, that phi predicts upon observing the data D. B. Solve. The revised model theta is applied to solve the task TD, and the loss value L theta, TD, is computed to quantify the performance on TD. 2 steps can be regarded as one black box function, which receives phi as an input and outputs L theta, TD. In other words, the task performance of theta depends on how phi gives attention when learning evidence text data. And phi can be optimized to minimize the L theta, TD. For this, the procedure of A and B is developed to corresponding steps of EQ 4 and 5, where alpha and beta are the learning rates for each respective update. Algorithm 1 presents the optimization of train attention, which involves sampling a data pair, D, TD, tilde operator D, predicting weights WD, phi left pointing arrow phi, D, and updating theta and phi through M iterations. The algorithm continues until phi converges. In summary, this paper introduces a novel method for continual knowledge learning that significantly improves over baselines through extensive experiments. The proposed methodology assigns weights to log probabilities of each sequence, approximating the importance of each sequence, and uses a metalearning approach to predict optimal token weights. The paper presents a novel approach to improving the continuous knowledge learning (CKL) capabilities of large language models. It introduces Train-Attention-Augmented Language Model (TAALM), which utilizes a metal earner to generate token weights for efficient learning. The authors also propose a new benchmark, LAMA-ckl, tailored from the LAMA dataset to assess plasticity and stability in CKL tasks. The metal earner, named Train-Attention, is trained using a task weight learner (TWL) method that adapts the token weights based on task performance. This process involves updating the base model parameters and then resetting them to their initial state after each update of the metal earner. The gradients of the metalearner's parameters are tracked during this process, akin to computing second derivatives. The authors conduct experiments on two benchmarks, LAMA-ckl and Temporal Wiki. For LAMA-ckl, they sample 500 units of TOLEARN and NOTTOFORGET sets from the LAMA dataset, focusing on time-variant and time-invariant relations, respectively. The evaluation setup involves training and testing phases over 30 epochs, with four main factors as evaluation indicators: top ACC, epoch, NFACC, and total knowledge. The results show that TAALM outperforms other baselines in terms of ability and speed of learning, achieving substantial improvements in CKL performance. The authors also compare their method with Row 1, a concurrent work on token selecting methods, and demonstrate the effectiveness of token-weighted learning for CKL tasks. Overall, this research contributes to enhancing the plasticity and stability of large language models in adapting to new knowledge and retaining existing knowledge. The paper presents a novel approach to continual learning, CKL, called Train-Attention, which significantly improves the performance of large baseline models in the LAMA-ckl task. This method utilizes token-weighted learning and metalearning to optimize the model's plasticity and stability. The authors demonstrate that their approach, TAALM, outperforms other baseline methods in terms of learning capacity, forgetting rate, and the balance between stability and plasticity. In the LAMA-ckl task, TAALM achieves an accuracy of 0.4290 on only 4 epochs of updating, which is 3.04 times higher than the second place, Row 1. The required epoch is only 25% of the second place, standard fine-tune. Furthermore, when comparing only the QLORA base methods, TAALM shows overwhelming performance in all dimensions, learning the most, the fastest, and forgetting the least. The paper also experiments on the original CKL learning benchmark Temporal Wiki, where models have to continually learn Wikipedia documents of serial periods and test on the corresponding TWIKIPROBES. Even with significantly smaller parameter sizes and computational resources, TAALM on 1B records the best compared to 7B baselines. This observation indicates that the proposed method outperforms other baseline methods even with smaller models. The results of the experiments and analysis indicate that train attention is optimized close to the upper bound, and the optimization through metalearning could excel human-labeled weight. The proposed method shows a considerable balance between stability and plasticity, making it a promising approach for future research and continual learning. This paper presents a novel method to enhance the performance of continual knowledge learning, CKL, in large language models. The authors demonstrate that their approach, Train-Attention, significantly improves CKL performance and is synergistic with other baselines. They also provide insights into why their method, LAMA-ckl, is more effective than traditional methods by analyzing the contrast between plasticity and stability. The authors conducted experiments on QLORA-based and K-adapter-based models, achieving state-of-the-art performance across all periods and both changed and unchanged TWIKIPROBES. This result aligns with the LAMA-ckl benchmark result, showing that their method has a substantial advantage on the CKL. QLORA-based baselines showed poor performance compared to K-adapter-based baselines, indicating architectural disadvantage. The authors also test TAALM optimized for LAMA-ckl on the temporal wiki, achieving the second best performance, indicating robustness across different distributions of tasks. They analyzed the reasons for this achievement, including the use of variant and invariant subsets, and conducting training over multiple epochs on a relatively small dataset. The paper discusses the limitations and potential for future exploration, such as the task specificity of train attention, the need for data-task pairs, and broader impacts on enhancing the practicality of large language models and saving computational resources for fine-tuning entire huge LLMs. The authors provide a comprehensive list of references to support their findings and discuss the broader impacts of their research. The paper discusses the LAMA-ckl benchmark, a dataset designed to evaluate the ability of language models to learn and retain knowledge over time. It is an extension of the LAMA dataset, focusing on the task of continually learning and remembering new facts. The authors detail the setup for the dataset, including criteria for selecting documents, assessing accuracy, and filtering units based on the performance of various models. The LAMA-ckl benchmark consists of two main sets: TOLEARN and NOTTOFORGET. TOLEARN includes units that are not present in the pre-training data but should be learned by the model. NOTTOFORGET, on the other hand, contains units that were present in the pre-training data and should be retained by the model. The authors also provide detailed statistics for these datasets, including the distribution of relation categories among TOLEARN and NOTTOFORGET sets. Furthermore, the paper highlights several key references related to the field of continual learning, metalearning, and language models. These references include works on focal loss for dense object detection, gradient episodic memory for continual learning, and the use of language models as knowledge bases. Additionally, the authors mention various techniques and models used in the setup of the LAMA-ckl benchmark, such as Tiny Llama 1.1b, Llama 27b, QLORA, and K-adapter. Overall, the paper presents a comprehensive overview of the LAMA-ckl benchmark, its setup, and its relevance to the broader research in language models and continual learning. It serves as a valuable resource for researchers working on improving the capabilities of language models to learn and retain knowledge effectively. This research paper discusses the relations of NOTTOFORGET and TOLEARN sets, as well as the evaluation setup details and train attention training details. The NOTTOFORGET set includes relations such as place of birth, place of death, subclass of, official language, original network, shares border with, named after, original language of film or TV show, has part, manufacturer, country of citizenship, language of worker name, continent, developer, capital of, location, native language, twinned administrative body, country of origin, and legal term and jurisdiction. The TOLEARN set includes relations such as instance of, position held, field of work, occupation, owned by, genre, headquarters location, record label, position played on team, speciality, member of, diplomatic relation, and instrument. The evaluation setup utilizes hardware with 8 RTX 3090 GPU, 24 GB, and hyperparameters including a global batch size of 64, learning rate of 1E4, Atom W optimizer, and max length of 512 tokens. A total of 30 epochs took 25 minutes of GPU time. Accuracy measurement is used as a metric to assess the efficacy of models in the task of label prediction, quantifying the proportion of label tokens correctly identified by the model out of the total label tokens presented. Train attention training detail includes the selection of LAMA units from both time-variant and time-invariant sets, specifically those with an accuracy below 0.5, while ensuring no overlap with the NOTTOFORGET and TOLEARN sets. The final version of the train-attention training dataset comprises a total of 4,166 units. The authors propose the schematic form to arrange the knowledge base triple into a human-readable sentence, which fits the one-directional feature of causal LM, as opposed to the descriptive form where important information sometimes appears behind the label tokens. They employ schematic form in training train attention, while employing descriptive form during evaluation. Training is conducted using small, tiny LAMA-1B, and large, LAMA-27B, models from the LLAMA family, integrated with QLORA. The authors find that using a large rather than small model for the base model, theta, results in faster convergence. On the other hand, employing a large or a small model for the train attention model, phi, made little difference in the aspect of the convergence step and validation score. So they adopt a large model for theta and a small model for phi while training train attention. In the test phase, they find that theta and phi are still compatible even though they don't share the same background model, as long as they use the same tokenizer. Therefore, they utilize small-size train attention for both small and large baseline experiments. The train attention head is initialized using a normal distribution with a mean of 0 and a standard deviation of 0.0001. Consequently, the weights generated by the initialized train attention are equivalent to the uniform weight where all Wi equals 1. This approach is adopted to observe the convergence of the L theta, Td, more clearly, ensuring that the loss value declines from the initial state if training proceeds normally. A single A182GB GPU is used, and the effect of batch size 16 is achieved through gradient accumulation. A checkpoint of 400 global steps is used, takes about 6 GPU hours. Of the 4,166 train data, 100 are used for validation. The learning rate of 2E4 and AtomW optimizer is employed for both the base model and train attention. The authors also provide details on the baselines, including QLORA and K-adapter. For QLORA, they employ LoRa R equals 64, alpha equals 16, NF4 with BF16 computation datatype. A total of 160 M parameters are expanded for the large, LAMA-27B, baselines. For K-adapter, they follow the previous CKL work of Jiang et al. 2022, with a total of 303 M parameters expanded. The trainable parameters are double the QLORA. Efforts are made to reduce the learnable parameters of K-adapter, but the authors observe that the current settings are the minimum level necessary for K-adapter to function effectively. In experiments, K-adapter demonstrates greater stability than QLORA, which could be partially attributed to its larger parameter size. They also employ the same quantization configuration of QLORA for K-adapter, NF4 with BF16 computation datatype. The provided pages detail the experimental results of the LAMA-ckl experiment on small baselines, specifically the performance of TAALM based on the small, tiny LAMA-1B architecture. Figure 10 and Table 5 showcase that even when compared to large, LAMA-27B, baselines, TAALM's performance is significantly better. This is further emphasized by the combination of Rs, TAALM, with other baselines, as presented in Figure 11, which demonstrates synergistic compatibility and improved performance. Table 6 and Figure 12 highlight that the combination of Rs and MixerView results in the highest top ACC and total knowledge among all variations, indicating a balanced approach between learning and maintaining. The trade-off between plasticity, TOLEARN, and stability, NOTTOFORGET, of all baselines is presented in Figure 13, with variations combined with our method positioned in the upper right quadrant, signifying minimal trade-off between updating and forgetting. Additionally, the pages report error ranges of the main experiment, conducted through 5 independent runs using different random seeds on the training dataloader. The results are displayed with error ranges at plus or minus 2 sigma in Figure 14, demonstrating the consistent performance of our method. All main experiments presented use the dataloader with random seed 42. The paper presents a comprehensive analysis of the trade-off between plasticity and stability in language models, utilizing the LAMA-ckl dataset. The authors visualize this trade-off through Figure 13, where they compare various baseline models, including combinations with their proposed method, using a large-scale architecture, LAMA-27B. The results demonstrate that the right and upper sides of the gray lines indicate more efficient systems where learning causes less forgetting. In Figure 14, the authors showcase the performance of large-scale baseline models on LAMA-ckl, with error ranges calculated from 5 random trials. This figure provides insight into the stability and plasticity of these models over 30 epochs. The paper also introduces the concept of descriptive form and schematic form for the LAMA dataset. The authors propose the use of the schematic form, as it better aligns with the unidirectional nature of causal language models, LLMs. This form rearranges knowledge triples into a more systematic and human-readable document, as shown in Figure 15. Additionally, the authors provide details on the temporal wiki experiment setup, including corpus setup, evaluation, and baseline setup. They discuss how learning only the DIFFSET results in better performance than learning the entire snapshot and employ heuristic filtering to remove empty texts and texts with high non-letter content. The evaluation metric used is the mean perplexity of object label words, with one dataset updated for only one epoch. The study adopts the LAMA-ckl task format to handle grammatical violations in the original work. The baselines and hyperparameters settings follow those of LAMA-ckl, which are based on Zhang et al., 2022. For training train attention, the DiffSet and Twiki probes data are paired, with a total of 5,235 pairs. Experimental results on Temporal Wiki show that performances in both changed and unchanged sets mostly move in the same direction when baselines are trained on the DIFFSET of each period. This is in contrast to the observation on LAMA-ckl, which exhibits a clear trade-off between plasticity, TOLEARN, and stability, NOTTOFORGET. This suggests that LAMA-ckl is a better benchmark for observing the trade-off between plasticity and stability. Table 7 presents the portion of task sentences in each changed and unchanged set that have evidence documents in each period of the training dataset, DIFFSET. An average of 8.0% of every unchanged set have evidence documents in the DIFFSET of the corresponding period, indicating that training on DIFFSET partially results in an improvement in the performance on the unchanged set. The unchanged set from the last period, T-Wiki-Probes 11-12, contains evidence documents in the DIFFSETs from all 3 preceding periods, suggesting that its supportive effect is cumulative. This is a complication factor for observing stability. Figure 16 shows the experimental result of small, tiny LAMA-1B baselines on the Temporal Wiki benchmark. The z-axis and y-axis correspond to the perplexity of changed and unchanged sets, respectively. Each color represents baselines, and the arrows represent the experimental result from each period. The start point of the arrow indicates the performance before training, while the end point indicates the performance after training.